Balancing chemical reactions. The law of conservation of mass is usually the thing that's used to explain why we need to balance chemical reactions. The law of conservation of mass says that matter cannot be created or destroyed, but only changes forms. This is true as long as we're only dealing with chemical reactions. With nuclear reactions, there's some different stuff going on there. So what we're saying in this won't apply to nuclear reactions. But in chemical reactions, what we're saying is that the elements that form the molecules are either breaking up or changing in some way so that they make new molecules. So the elements themselves are not disappearing, they're not appearing, they are just changing the way in which they're combined. What that means is elements are not created or destroyed but only changing forms, means that the number of elements of any type, hydrogen, oxygen, whatever it is, before the reaction has to be equal to the number of that kind of atom after the reaction. One way to think about this is the atoms just aren't going anywhere, right? So let's look at a chemical reaction here and see if we can see what we're getting at. H2O goes to H2 plus O2. So if we imagine this chemical reaction, I'm going to use some colors here to hopefully help me show this. For the sake of this argument, we're going to say that hydrogens are these little red balls. So we had an H2O, and we'll make oxygen, these big blue ones, okay? So there's my H2O molecule right there. See, two H's, two little red ones, combined with one big blue one, one oxygen, is going to, so there's the reaction, H2, so the two hydrogens are going to stick together like that. Ooh, like that. There's two little hydrogens. They start to look like one. Hopefully that's clear. And two oxygens. So there's one oxygen, and there's the other oxygen, and those guys are sticking together like that. So these two H's break off and form their own little thing, and then the oxygens form their own little thing, their own little molecule. See, the atoms that make up the molecule are rearranged into new molecules. That's what a chemical reaction is. The problem is, if we look at this carefully, what we're going to see is that there's an oxygen atom here that's appeared out of nothing. See, over here we had two hydrogens and one oxygen, and over here we have two oxygens. Where did the second oxygen come from? So if we say matter cannot be created or destroyed but only change forms, we can't just create this oxygen atom out of nothing. What that means then is that the number of oxygen atoms before the reaction should be the same as the number of oxygen atoms after the reaction, and that's not the case here, so we need to do something to fix that. Looking at this, if I need two oxygens to form the diatomic oxygen after the chemical reaction, I must have had one more water over here to start with. See, now I have a spot where both of those oxygens could have come from, and now the fact that this guy exists isn't a problem. He hasn't been created. See, one oxygen and two oxygens is now going to two oxygens, and we're okay. The problem we have now is now we have 1, 2, 3, 4 hydrogens, and we only have two hydrogens over here. So if this happened, clearly we would also produce a second diatomic hydrogen gas, just like that. So now if we think about it, we've got two waters. The two oxygens of those two waters come together to form a diatomic oxygen. And the two hydrogens and two hydrogens then can form their own diatomics off on their own. And this makes sense because the number of each element, the number of hydrogens or the number of oxygens before and after the reaction is the same. What that means in terms of the overall chemical reaction, if we think about it, is that now we recognize what really has to happen here is we have two water molecules reacting to form 1, 2 diatomic hydrogens and 1 diatomic oxygen. You don't need to include that 1 if nothing's written there. I would assume that it's 1, but for now, while we're practicing balancing, we'll put those 1s in just to make sure. So that's that. That makes sense, right? These two form all of these, and that way there's no matter being created or destroyed out of nothing. To make sure that this is true, then one simple tool we can use is we can do a before and after chart. And that way, when we have a chemical reaction, we can figure out if the number of atoms before and the number of atoms after the chemical reaction are the same. I'm just going to keep using some simple examples here to illustrate this a few more times, and then hopefully we'll see it. So here we have sodium reacting with chlorine gas. Sodium as a metal can hang out totally on its own, so that's fine. Chlorine gas, Cl2, remember he's a diatomic, going to form table salt, or as we know it, sodium chloride. And I can imagine the crossover here, it was +1 to -1, so I crossed them over. And I got a 1-to-1 ratio, or I don't have to include it. Now, again, I'm just going to draw one more of these here. I had a sodium atom combining with 2 chlorines, the diatomic chlorine, to form sodium chlorine. The problem is here I have 2 chlorines, 2 of these, and only 1 over here, so that's obviously not good. So if I was thinking about chlorine, I have 2 to start and 1 here, and that means that we're not balanced, or it's not right. So obviously I need another sodium chloride so that I can get my chlorine number right. So that's 2 of these molecules. So now, before and after, I have 2 and 2, so I can say that's balanced, as long as I don't do something to mess that up later. I won't have to in this example. But now, if I consider my sodium, I only have 1. Oh, what did I just do? There we go. I just have 1 before the reaction, and I have 2 after. 2 after. So obviously this can't stand. Now this sodium atom is coming out of nothing. So that's pretty easy. I can just add another sodium over here. I don't have my red color, but you get the idea. I'll do it right. So I can just add another sodium over here. And then what that means effectively is I have 2 sodiums going into the reaction, which gives me 2 and 2. And now I can see that element's balanced, and now all my elements that make up this chemical reaction on my before and after chart are balanced. You don't have to do before and after charts. It's just a way to check at the end to make sure that you've gotten it right. And when you get better at these things, you won't bother with this. But for now, it is a nice little tool that you can use if you're having trouble. Alright, I'm just going to give you, in this video, 3 tips that are going to make this a little bit easier. So the first tip I'm going to give you is when you're trying to decide, you have a big reaction like this. I've got hydrogens, I got oxygens, I got potassiums, I got sulfurs. When I'm trying to decide who I should start with, I should always start with metals or polyatomic ions or uncommon nonmetals. And specifically what I mean by uncommon nonmetals are stuff like the sulfur in this example. The reason is these tend to appear less in the chemical reactions and less of the actual molecules. And what that means is they'll be easier to get balanced first, and they're less likely to get messed up when you go to try and balance other stuff. So I could start here with potassium or sulfur. If I look at the sulfur, he's 1-to-1 in ratio, so that's not worth worrying about. There's 1 sulfur going to 1 sulfur, so that's fine. But if I look at my potassiums, I have 1 potassium going to 2 potassiums. So I better put a 2 on here. Now, often this is the case. If I balance one thing on one side of the reaction, I should flip over to the other side of the reaction to try and balance the next thing. If I look at my oxygens, they look balanced as is, but if I look at my hydrogens, I have 2 plus 1. So that's 3 going to 2 over here. And that's looking like it's going to be a difficulty. So let's see if I can figure out what to do with that. Oh, I should have paused this video. So if oh wait a minute, my oxygens aren't balanced, sorry. 2 times oxygen leading to 1. So I looked at 1 and 1 and thought it was okay, but somehow when I looked at it, I ignored the coefficient, which is the whole point. So oops. Okay, so this is going to make sense. I paused there for a second because I wasn't seeing it, but here we go. 2 oxygens going to 1 oxygen, so I need 2 of these molecules. And hopefully, if this chemical reaction is right, the hydrogens will work out now. 2 hydrogens going to 2 hydrogens leads to 4 hydrogens on this side and 4 hydrogens on that side. Let's make our before and after chart just to make sure that this is correct. I'm pretty sure I have it right now. So I started with potassium. I have 2 of them, 2 of these KOH molecules on this side. I have 2 potassiums on this side, so that's 2 to 2. Then I looked at sulfur. I have 1 and 1, so he's happy. The next atom I looked at was oxygen. 2 of these potassium hydroxide, that gets me 2 oxygens. 2 of these waters, so 2 to 2 again. And finally, hydrogens. Hydrogen appears in so many different molecules here, I left them to the end. 2 plus 2 for a total of 4 and 4. And so I can say, since all my before and afters are the same, this chemical reaction is balanced. Tip number 2. Check to see if the polyatomic ions stick together. If they do, think of them as one element. So the polyatomic in this chemical reaction is SO4. And so what I'm looking for is after the chemical reaction, is he still SO4? Since he is, I don't want to think of it as sulfur and 4 oxygens, but instead I'm going to think of SO4 sulfate as one thing, and that thing needs to be balanced. If that's the case, it's usually a really good spot to start with balancing. Here I have 1 of them, here I have 3 of them, so that must mean I need 3 of these molecules to make this work. Now I have 3 sulfates going to 3 sulfates, so sulfate's done. Looking next, I'm going to balance the aluminums, because they're, I don't know why, that's what I'm going to do next. Aluminum and aluminum, so I have 1 going to 2, so I'm going to have 2 of these molecules. So now this molecule and this molecule and this molecule are sort of balanced with each other, and so I'm going to use this guy to balance out all the KCl's. 2 Ks times 3 of them in total gets me 6 Ks, so that means I need 6 potassiums, and just to make sure, 2 times 3 chlorines means I have 6 chlorines, which leads to 6 chlorines, and I'm okay. Right now, because I'm starting off on this, I'm going to do another before and after chart. But here I'm going to treat sulfate as if it's one thing. So here I have 3 going to 3. Potassiums, I have 6 going to 6. Chlorines, I have 6 going to 6. And finally, aluminums, I have 2 going to 2. And so my equation is balanced. Alright, the last tip for this video anyways is going to be to leave oxygen or hydrogen to the end. They can tend to be in a lot of species or a lot of the molecules, and so the more molecules they are in, the later you should try and leave them, because the more likely if you start with them that when you go to balance something else, you're going to mess them up again and have to start over again. So in this case, I'm going to start with my carbons. I have 3 carbons. Over here I have 1, which means I need 3 of these molecules to make it work. 3 goes to 3. Now I'm going to do hydrogens next. I'm going to do hydrogens next because I'm looking at oxygen over here and I know I can finish with him. So I've got 8 hydrogens here and 2 hydrogens here, which means I can use 4 hydrogens. And now 3 times 2 for 6 oxygens here, and 4 times 1 for 4 oxygens here. That gets me 10 oxygens. 10 oxygens means I need 5 of those molecules to make it work. Doing my before and after chart. Carbon, 3 to 3. Hydrogen, 8 to 8. And oxygen, 10 to 10. So this is one of those things where at first you're not necessarily, when you see a new chemical reaction, going to see where to attack it. But after you've done a whole bunch of these things, with these 3 tips to get you started, you'll start to just see where you should go to start with these chemical reactions. Getting them balanced is going to be the first step in a whole lot of problems that we're going to do for the whole rest of the course. So this is a skill we really need to make sure we're done. So my last tip here is you are going to need to practice balancing chemical equations a lot until you are 100% sure that you do not have a problem with this skill.